The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, I wish you all had a good weekend. And just recap of last lecture is a little bit extra than last lecture. But say what we solved is a problem of heat conduction along a two-dimensional thin film. And the Boltzmann equation written for the deviation function g is f minus f0, right? So g is f minus f0, and we say g because the boundary in the y direction, so there are constraints change in g in the y direction. So we have the v cosine theta. V cosine theta is the actual direction of the photon propagation, and so we have on the left hand side is a function of y, and then on the right hand side is a function of x, right? The f0, because I have f0 for photon is exponential h omega kt minus 1. So t is a function of x because I was considering heat conduction along the x direction. And if you do electron transport, which we didn't do last time, you have to keep this term, the fourth term, and that's when we did in chapter 6, the thermoelectric transport, we treated both terms. But see, the point is, if you look at transport along the x direction, and on the right-hand side is a function of x only. So I have a first-order differential equation for the deviation function in the y direction with right-hand side is x-dependent. So because of that, the right hand is essentially constant because the left-hand side is a function of y. So when I did the integration, I found the heat flux. And what I'm giving here is more than I showed in the last lecture because this solution is Fuchs-Sontheimer. I checked the name, Heimer solution. Okay? And Fuchs-Sontheimer originally solved for the electron transport. So these were, in the original paper, electric conductivity ratio of the thin film divided bulk is, say, 1 minus. So it's reduced. And this reduction is this integral mu is cosine theta. So it's 0 to 1. And the p is a specularity parameter. P, specularity parameter. So if it's a p equals 1, it's a specular. P equals 0 is a diffuse. So you can say if it's a specular, 1 minus p is 0. So it's more like a waveguide. There's no reduction if it's a specular interface. But the p equals 0 is diffuse, so you will get reduction in the thermal conductivity or electric conductivity if the interface scatter electron photon diffusely. And but say it has been actually really difficult to say what is this value of p. And so far, the best model people use was still a result that derived by Zeeman in 1950s. And this p is related to the surface roughness and the wavelength of the photon or electron. So it's an exponential function, and in fact, you see in the front is 16 pi cubic. So that's a pretty large number. Typically in optics, when people say a surface is rough or is a specular, for optically smooth surface, is typically roughness is less than 1/10 of the wavelength, right? So you can say if the roughness is less than 1/10 of the wavelength, this P is the it's getting close to, right? This one is when it's very large, very small, it's close to 1. That's specular. Okay, so this is a Fuchs-Sonderheimer solution, and that's the for diffuse for the electrical and thermal conductivity along a film. And we assume that the length of this film is very long. So if you go to look at the literature, there are a lot of papers publishing on measuring thermal conductivity of thin films or nanowires. And there are also refined model of wires of different cross-section, whether it's a circular, whether it's a rectangle. And the people try to solve the Boltzmann equations. And I mentioned in the last lecture, even now there's still some result on the wires puzzling, and people still writing what could be deviation from the Fuchs and Sonderheimer solution. Okay, and historically, this is a Casimir. What Casimir did is really say he explained without the Solomon-Boltzmann equation, just no internal scattering, you have rough surface, and he say, okay, if you have rough surface, because the scattering is diffuse, so you have effective reduction in the mean free path of the heat carrier, the photons, and with that, he was able to explain why thermal conductivity at low temperature is proportional to specific heat. The mean free path is limited by the sample size, and the low temperature, say the thermal conductivity 1/3 CV gamma. So when the mean free path is the sample size is proportional to the specific heat, which is T cubic. So this is the Casimir say started. So that's last lecture is a film conduction along the film. Just one more comment. You actually could say that recently there's some paper on the thermal conductivity of carbon nanotubes, and it turns out because some nanotube the mean free path is even longer than the length of the tube, so there is an additional size effect at the two ends of the tube. Okay. And what we're going to do in today's lecture is look at the other direction. So heat conduction perpendicular, right? Let's say transport perpendicular to film. Okay, and if I look at the now the problem is, and if I have a temperature difference, I have to be a little bit ambivalent at this stage. What's this temperature really mean? So I have a T1, T2, and in the thickness direction of a film. And this is my y, right? And again, I have the mean free path is could be longer than the film thickness. And then what's my effective thermal conductivity, right? And you can ask the same question, what's my electrical conductivity? And also their solution for radiation, photon transport. All those are under the same equation. And I write down the Boltzmann equation under relaxation time approximation. So here I have dVy dF dy plus equals minus F0 divided by tau, right? Because in this case, my equivalent temperature changes as a function of y. So T is effectively a function of y. And f0 now through the temperature dependence exponential h bar omega kt minus 1. Right? So you can say what the difference from the previous problem is in the previous problem, the relaxation time is a function of x, but the size effect happens in the y direction. Now, my temperature is a function of y, and the size effect happens in the same direction. So my solution will be more complicated than the previous one. And let's solve this problem. And I will first do Vy, again, say any photon transport direction, let's say along this direction, and the angle to the y direction is theta. So I will do this Vy is V cosine theta. Okay, and V times tau, I will normalize, gives the mean free path. So mean free path is V times tau. And I define a non-dimensional variable eta equals y over mean free path, right? And in the previous one, could say equals d over mean free path, so that's the normalized to the thickness. But this is an arbitrary coordinate y. And if I do this, I write the Boltzmann equation now into mu, which is a cosine theta. Mu equals cosine theta, that's directional cosine. And I have df dy plus f, I move to the right, not y, d eta. The mean free path now is v times tau. So say eta is y over mean free path. So I long dimensionalize my equation. On the right-hand side, then I have f0. Remember, f0 is a function of t, and t is a function of y. I do not know that t. So now if I say it's a function of y, is also a function of eta. So I have the f is a function of eta. f0 is also a function of eta. Now, this equation is a little bit harder to solve than the previous one, because in the previous one, the right-hand side is a function of x, the left-hand side is a function of y. Now, in the current one, both left and right-hand sides are function of eta, right? And to solve this first-order differential equation, the trick you do is first you solve a homogeneous equation, eta df d eta plus f equals 0. And here you'll find out this one gives you f eta is a function of say exponential minus eta over mu. Right? That's the solution for homogeneous equation when the right-hand side is 0. Okay? And now when the right-hand side is a function of eta itself, you change that say into an unknown function you want is a function of eta. So that's the standard way of solving. Now rather than say is a constant, say is a function of eta, you substitute this back into the original equation, right? You'll find out this term will drop out. So what I have is mu exponential eta mu dc d eta equals f0, which is a function of eta. So this is when you substitute this back into the differential equation, this term drops. The other term, you can take derivative of this, also drop. The c term I cannot, so it's there. Right? And now because this is a function of eta, this is a function of eta, so I can integrate. So what I have is say itself, dc d eta equals f0, which is a function of t eta, right? That's a function of t. and 1 over mu exponential eta mu. So I integrate, I will get say is another integration constant, right? That depends on where I start. So this is my eta 0 to eta, and 1 over mu exponential eta prime, and the f0 eta prime, d eta prime. So this is my solution for this constant, which is now no longer constant, is a function of eta, and that's my solution. And I combine this, say, back into the original, my solution for f eta, but it's also a direction function of mu, is C0 exponential minus eta over mu. That's this term. Now this term is also multiplied into this term. So what I have, because this one is integrating eta prime, so I can put that in. So what I have is eta 0 to eta 1 over mu exponential minus eta prime mu f0 d eta prime. Okay, so that's my general solution for this original differential equation. You say that I didn't go to find the deviation, I just solve f directly. And for the previous problem, this one, I use a deviation function, but you don't have to. You can still solve f directly. You get the same result. It's just a math difference. OK. And again, I need to now use the boundary condition to solve for C0, right? And for each mu, now for the problem, each mu is a cosine theta, right? So that for each theta, I have, say, a different origin. So if for theta between 0 to 90 degrees, I have y equals 0, this surface. If it's a diffuse, the temperature TE1 that goes out is isotropic. So, and then for 90 degrees to 100 degrees, it's actually coming from this surface, right? And again, say it's diffuse, the temperature as it goes out is TE2. This is what I call emitted temperature, right? So I go to do the condition where eta equals 0. So I start with eta 0 also at 0, and this one drops out. So what I have is f for mu is less than 1, larger than 0. That's 0 to 90 degrees. F eta mu is f0 TE1 exponential eta to mu plus 0 to eta 1 over mu exponential minus eta prime over mu f0 d eta prime. Okay. So unfortunately, the difficulty is this is almost like the simplest heat conduction problem, right? It becomes very involved. So this is the solution for 0 to mu to 1. I will put it a positive. That's the from bottom to up, forward propagating. And similarly, for 90 degree to 180 degree, I have a solution, right? For 90 to 180, so mu is negative 1 and to 0. That's a theta less than, say, 180 degree, larger than 90 degree. So backward propagating from top surface to down. And my solution, f prime eta mu, then your say FTE2. That's the corresponding Bose-Einstein distribution for the photons that are coming into the domain with the characteristic temperature TE2, right? So this is a F0 TE2 and the exponential cosine minus eta over mu. This is the effective boundary effect. Here is eta over mu. It's a negative. It's an exponential decay. So what it says is, if my photon is propagating in this direction from the boundary, at this point, right? Because the scatter, it decays, and that distance, the ratio, the decay that is exponential, cosine minus eta. So that's the really d minus y. So that's this section, and divided by cosine, divided by mu is cosine theta. So that's this distance, right? So it's really because mean free path. So it's how much distance travel over mean free path exponential. That's the decay because they scatter out. The boundary terms get scattered lost to the internal. And then the next term is cosine to eta and 1 over mu exponential minus, here I have to be careful because this is a cosine to eta, so any d eta prime term, I have to make sure this is a decay. So I have eta minus eta prime. That will be, well, let me see whether it's positive or negative. So any term in between, this will be negative, this is negative. I should have another negative sign in the front, and the F0 eta prime. So this is how I look at the equation, why I see whether my solution is reasonable. What I have here is I'm looking at a certain point, this point in space. I look at the distribution in this specific direction. And what it comes, one part is coming from the wall, the boundary, and that part is exponentially scattered out. So that's the first term. That's a decay term, right? This term is decaying. The other term is along the path, every point is re-scattered into this direction, right? Like say emission into this direction. So because of this, I have contribution. The contribution from this point, that's F eta prime, F0 eta prime. That's regenerated. And the distance is here, the difference. So this is a regenerated photon. And this is the distance divided by cosine theta. So the real distance, right? Distance, the y direction coordinate divided by cosine theta, that's the real distance between this source point and the point I'm interested in. And again, during this travel, there's a scattering out. So that's why the exponent I have to make is make sure this exponent at the end is negative. Eta minus eta prime, because my this is eta cosine. So the eta prime is between eta and cosine. So this is negative. And mu is negative. So I put the negative sign. That should be my correct solution. You can go to actually check the mathematics, right? So now I have the distribution function, and my challenge is, remember this one, F0, is a function of eta itself. I do not know, right? It's inside the integral. And what I have is a long local transport. It's not like a Fourier law of heat conduction where Q equals minus K dt dx, right? You see, this is a local transport because the heat flux is proportional to local gradient. It doesn't depend on quantity in other places. Of course, they are all coupled, but local flux is only local proportional local gradient. what I have here is the flux at this point depends on every point along the trajectory. That's why I have the integral, path integral there. Okay? So this is the problem when you go to nano, your transport becomes coupled and it's non-local. Okay? And now once I have F, I can solve for my flux same way. Q equals 1 over V. You sum up all polarization, Kx, Ky, Kz, and Vy, h bar omega F. Right? That's always the starting point when we try to find out what's the net flux. Here is for heat flux. Again, charge flux, momentum flux. You do. This is how we start. We sum up all possible modes, quantum mechanical or classical modes, and to get the, and of course, given the quantity h omega each mode carry, quantum state carry, and the group velocity. So if you do this, and you see we have to convert this summation into integration, right? And I will actually split this into two terms, positive term and negative term. And positive term are the ones that goes forward. Negative terms is going from the other boundary going downward, right? And then we can look at what the expression after I convert this into from integration into summation into integration. So positive term is actually 0 to pi d phi. So this is again, I'm changing this into a spherical coordinate, right? And phi is azimuthal angle, and 0 to 90 degrees sine theta, d theta, right? Theta is the angle, the polar angle under my coordinate system. And then I have integration over frequency, 0 to max frequency, and h bar omega. So that's here, V cosine theta, that's Vy. And say when I convert summation into integration, I have density of states, d omega over 4 pi, because this d omega is integrated originally for 4 pi isotropic case. And then I have F plus. That's the solution I had there. Here, F plus is a function of both mu and eta, and then integrate over frequency. Okay, so that's the flux here, right? And if you plug in your solution for F eta plus, what we have here, and we can write it into. So I'll give you the final expression. And this one, what I have is 2 pi I0 T E1 plus, say, times E3. And this E3 is, again, the integral exponential function that we introduced in the last lecture, and 2 pi 0 to eta I0 eta prime, and E2 eta minus eta prime d eta prime. Right? So I have to now say introduce this I0. I is a transformation, so I0 is just integration of h bar omega, and V times d over 4 pi, and F0 d omega. So sometimes say this is called intensity. But it's just a result coming from the simplification in notation. And in fact, say in photon transport, this intensity is widely used, but for electron and photon transport, this is not widely used. I remember when I first wrote the paper and submitted phase review B, and the reviewer come back, what is intensity, right? And is a scalar or is a vector? And I mentioned before, this relates to F itself. Is F itself a scalar vector? It has directionality. It depends on space. But it's scalar because it's a scalar in the phase space, right? And the directionality came from the velocity component in the phase space. So this is again, it's just it's a scalar. So this is the positive heat flux, and you can integrate the F minus and to get the negative heat flux, and the net heat flux is the difference of the two. So if I write the net heat flux, let me write it down, and you will get the net heat flux Q is Q plus minus Q minus, and what I have here is 2 pi and I0 TE1 E3 ida. That's the first term. And plus what we just wrote down, 0 to ida, I0 ida prime, and the E2 ida minus ida prime, d ida prime. So that's the plus term. And then I have minus term, minus I0 TE2 E3, and cosine minus ida, minus ida to cosine, and I0 ida prime, and E2 ida prime minus ida d ida prime. So this were the end result after you substitute Q plus, which we derived, and Q minus, which we didn't write it down. Okay? So this is your net heat flux. This term comes from boundary. This term comes from boundary. These terms coming from internal points, the non-local part, that's the source, and how much they contribute to the net flux at the location eta that I'm considering. So this one, right, this is a Q is a function of eta, the different locations along the y direction. Yes?
How can you know the effective temperature distribution inside?
I don't know yet. I didn't tell you I know. That's what you want to find, right? So this is the complexity of solving even the simplest ballistic problem, non-local problems, right? So what I'm going to next do, this is you ask the question, so how I'm going to find this out, right? So my next step is to find this out, I have to say the heat flux, either heat flux if there's no internal heat generation, whether there's internal heat generation or not, right? Remember, I'm doing the steady state problem. You will see that based on the treatment, when I do transient, all my analysis doesn't work. Okay? So, well, here the analysis is fine, but see, when my next step is doing the, when I say there's a case when I'm dealing with no internal heat generation, right? And in fact, we wrote a paper to compare the case when there is internal heat generation, what's the difference? So when no internal heat generation, no heat generation, and in this case, what I have, Q is constant, right? If Q is constant, I can do dQ d ida equals 0. So because I don't need to find that constant yet, right? So with that, I take this dq d eta equals 0. I will find the equation that actually has the unknown eta 0, say I0 that I want to find. So you go to take the derivative. Let me just repeat here. What is the E, right? En, the nth order integral equation equals, say, t n minus 2 exponential minus t over mu, and d, no, not t, this is mu, and d mu 0 to 1. This is my integral equation, integral function of order n. So I have E3, and here is E2. You can substitute it. So if I take a dq d eta equals 0, what I have is an equation I0 T1 and E2 eta, and plus eta 0 TE2 and E2 cosine minus eta, and plus 0 to eta 0, eta prime, I0 eta prime, E1 eta minus eta prime absolute, d eta prime equals 0. Okay, I didn't go step by step, but say when you take a derivative, E3 becomes E2, and E2 becomes E1. And this two half integral, right? This is 0 to eta, eta to cosine, is combined right into 0 to cosine. Inside there is I0 eta prime, but E1 now has an absolute sign because it changes sign when eta equals eta prime. So I put an absolute to simplify the notation. These are actually two terms. Okay? So now this is the equation you need to solve to actually find, given the boundary condition, on one side is TE1, on the other side the TE2, and the mean free path, film thickness that determine cosine, right? And then you need to solve this equation to find what is I0 at each point. I0, remember, is related to my temperature, right? I0 is related to F0 because this is the photon property density of states, frequency omega, which you know from the solid that you're dealing with. But F0 is a function of T, right? T is what I want to find. So you really have to solve this to find I0. From I0, you find T. This is the complication of heat conduction, non-local heat conduction. Okay? And it's an integral equation. And how many of you have dealt with the integral equation before? One. Right? So what you need to find is what's inside and how to solve integral equations. Right? And I can simplify this a little bit just to make the equation nicer. So let me introduce a variable. Theta is a function of eta, and that equals non-dimensionalized. So I have I0 eta minus I0 TE2, and I have here I0 TE1 minus I0 TE2. So I introduce this non-dimensional temperature, or you can say it's temperature or non-dimensional intensity, right? And then say it turns out there is also non-dimensional heat flux, which is the Q, the heat flux over pi I0 TE1 minus I0 TE2. So this is the corresponding non-dimensional heat flux. And with this theta, I can rewrite the equation. You basically, you substitute this I0 into here, and using the reverse back, and you can rewrite the integral equation into a more standard form. This is what you have is 2 theta eta equals E2 eta plus 0 to cosine theta eta prime and E1 eta minus eta prime. And this is d eta prime. So this is the integral equation. A lighter form, right? Theta and is inside the integrand, and there is also long function, non-zero long function, and this is called the Fredholm integral equation of second hand. Integral equation of second hand. Okay, and when I try to solve this integral equation, I went to numerical recipe, and people will teach you how to solve these integral equations. There's no analytical solution, and what you have here, E1 is often called, this is the kernel, right? That will be multiplied to the unknown function. And in the old days, for this kernel, people, because when the computer will become powerful, before that, for this kernel, people try to get the analytical solution by approximate the kernels. And but nowadays, you can solve this integral equation relatively easily. And the way to solve the integral equation is going back to think, if you want to do an integral of a function, what method do you use, right? The simplest method of solving, doing a numerical integral is trapezoidal method, right? So whatever function this theta is, this is my eta, this is the unknown function I want to find, right? Let's say this is my theta eta. And I divide this domain into endpoint. Say here I have, say, you can do the trapezoidal is equally divide them, right? And for each of this, say, trapezoid, you take a trapezoid, you have your area is the width times height. So I can do my approximate this integral by discretization, 0 cosine theta eta prime and E1 eta minus eta prime d eta prime equals, and trapezoid typically have two ends special because it's only half cell, right? So I have theta 0 and E1 eta, and this is when theta prime equals 0, so eta minus 0, that's eta itself is positive, so I don't need the absolute sign. Delta eta over 2, so delta eta is the separation of the points, right? And I have similarly at the other endpoint, theta cosine. So this is when eta prime equals this endpoint. I have this half cell only. So I have E1, and eta prime equals cosine. So I have cosine minus eta, and then say theta at the say theta point. And then the rest is delta eta and 1 to n minus 1 point in the center. I have theta eta say I, theta I, eta I, E1 eta minus eta I, So I'm discretizing eta prime, right? So eta is the point I want to find, right? Theta eta, the eta, say eta is any point of this equation is satisfied. Okay? So this is my discretized term here. And I want to, if I look at this, I have how many points I have, I want to find. I have theta 0, theta eta, and theta I, 1 to n minus 1 point, so I have n plus 1 points. Right? I want to find the theta I at I equals 0, 1, to n point. So I have a total n plus 1 points. Okay? Now you look at the equation, you substitute this discretized term into an equation, and this should be valid for any eta point. And you know you need an n equation because you need an n plus 1 equation because you have n plus 1 unknowns, right? So how you get that n plus 1 equation? You let your eta equals 0 delta eta, 2 delta eta until to the total n point. So you set your eta equals eta I. That's the discretization point. And then you'll get the n plus 1 numerical equation. And with that, you can invert the matrix to find what your theta I is. And this matrix is different, but then you solve Fourier heat conduction equation or Levi-Stokes equation. In that case, your matrix is mostly 0, except the diagonal and the two lines say adjacent to diagonal direction. This matrix is typically a full matrix because every term is non-zero. Okay, so you need to invert that matrix to find the temperature distribution, or in this case is long-dimensional intensity distribution. Okay, but there's one more trick you put in there, one more problem. That's this kernel. Most of the time when you solve integral equation, this kernel has a problem. It's a singular. And this is the case if you say when you do your here, when eta equals to eta I, right? What is E1, 0? When eta equals to eta I, right? E1, 0, if you look at my definition for the integral function here, right? N equals 1, so mu and 0, t equals 0, so it's 1 over mu d mu. So what I have is 0 to 1 and 1 over mu d mu. 1 over mu d mu is log mu. What's the value at log 0? Blows up. So I have a singular kernel, and I have to deal with that problem when I solve integral equations.
Do you use the principal value of or like going like 1/2 principal value?
No, yeah, you don't need to do that. There's a trick to do it. Okay. So the trick to do this one is actually 0 to say theta eta prime E1 eta minus eta prime d eta prime, right? That's what we want to do numerically. And what I'm going to do is actually I'm going to do, because this is theta, I'm going to subtract this point out. Okay? So I don't do that integration. I do theta prime minus theta eta E1 eta minus eta prime d eta prime. So this I subtract that theta eta. And of course that means I will need to add that back. So theta eta is not an integration variable. So I'll do theta eta 0 cosine E1 eta minus eta prime d eta prime. Okay? So this is just an equivalency, right? Because this term I subtract, I add. And because I'm doing this, theta eta can pull out this integral, the kernel itself can be analytically done. And if you do this integration, you find that it doesn't blow up. Okay? So that's the trick. And this one, if you do it, this term, in fact, you will say this is mu 2 mass exponential mass eta over mu, and mass exponential cosine mass eta over mu. So this integral doesn't blow up, so I solve this singularity problem. And that means your discretization, it's a little bit more complex. You have to write this carefully to deal with this point. But overall, now you have, by incorporating those tricks, you can solve this integral equation. And you have to do it yourself to really, there's nothing, you all know MATLAB. MATLAB is good at the inverting matrix. When I do it, I have to write the Fortran code. That's what I know. And, but there are also libraries to call for inverted matrix. So this is the trapezoidal method. And if you use trapezoidal method, you need a lot of points. This for integration, trapezoidal is the most straightforward, but it's the most inefficient, right? So as I said, I'm not good at really numerics, the coding. So, but the one that I can reduce the number of integration I know is if I use this quadrature method. So if I want to use the quadrature method, fx dx, any integration, and there is one popular quadrature, not always good, I equals n, say equals 1 to n. So this quadrature does not divide the integration domain uniformly. It actually chooses finite number of roots. In this case, I have I equals 1 to n. So n, any number you take, and it will find the optimal root of this quadrature and give away. So this is xi. The xi, this solution depends on what quadrature you choose and how many order your n is. Okay? And then you give it a weight to that point. And so a popular way is the gauss-legendre quadrature. So when I wrote all my code was written using gauss-legendre quadrature. And sometimes it works well, other times it may not be that efficient. And, but there are other quadrature you go to look at the numerical integration books. Okay? And so with all this, the math part, let's look at the result that you are supposed to get. Look at the solution. So what the solution look like? So I have the problem I'm dealing with in the current, say, the original configuration I draw. This is my y direction, right? And I use a long-dimensional coordinate. Eta equals y divided by mean free path. And so if I plot the solution, this for this long-dimensional intensity theta eta, okay, and I'm going to actually not use the eta. Here is a little bit confusing. What I'm going to do is y over d, so that I can plot all the lines between 0 to 1. Okay, d is the thickness of the plate. So I have 0 to 1. Okay? And this long dimensional, so the first is 1. The maximum is 1. And minimum is 0. So one solution, this is a Fourier solution. When the mean free path is much smaller than the thickness. So what I have here is this one is say equals d over mean free path, right? So say is the non-dimensional thickness d over mean free path. When this one goes to infinite, that's the thickness much larger than the mean free path. And this profile is linear, and that's what you would expect from Fourier law of heat conduction. This is a diffusive, the local diffusion solution. Now, in the other case, when this Ksay goes to 0, what it means, there's no scattering inside, right? You will be ballistic, so you will have a solution flat. It's going to 0.5. Okay? So this is the other limit when Ksay goes to 0. You have ballistic transport. So why is that? And although I say here I'm solving using the photon as example, but say this is valid for electron and for molecule, for photon, and for photon. So let me take the example I talked before. This is the case when I have radiation transfer between two parallel plates in vacuum. Right? There's no scattering inside for photon because Ksay is say goes to 0. That means d is very small compared to mean free path. There's no internal scattering. When there's no internal scattering, what you have here, recall we said that here is sigma T1 force power. Here is sigma T2 force power. Right? That's what you will get if you do I0 integration. Right? You recall we did the I0. If you put the for black body radiation integration from 0 to infinite, you get sigma T force power. That's the Stefan-Boltzmann law. Okay? So in this case, I do not have any scattering in between. I do not have equilibrium in between. Very long equilibrium. But I'm forcing my Boltzmann solution to get a temperature, right? This temperature is the equivalent temperature when I have this imaginary absorber that absorb this on this side, absorb sigma T2 force power, on the other side absorb sigma T1 force power. So equivalently, the absorber temperature will be the average of this two force power divided by 2, right? And it's everywhere is the same. So that's why you say in this limit, my solution is flat. Okay? And now in between, I have a jump, a discontinuity at both sides. And this will be almost linear, not exactly. This is where it's in between when you go between 0 and the infinite. That depends on how large is the Ksay. So what's interesting out of this is at the boundary, there's a temperature discontinuity, temperature jump. Okay? So this is originally, this is say TE1 is here, that's normalized to 1. But say what I say here is inside the material, when I use the Fourier law to find the equivalent temperature, when there's scattering, even at the wall, the temperature, local temperature is different from TE1. So this temperature discontinuity, temperature jump, is a very tricky point. and when we discussed chapter 5, I mentioned this, and here it reappears because my solution now is more general. I can solve for any, in the chapter 5, there's no internal scattering. I see there's a jump. That's 0.5 from 1 to 0.5, right? So what I'm dealing here is, first, it depends on what problem you're solving. If it's a radiation problem, this is physical. If it's a conduction problem, what I'm talking is unphysical. It's a wrong definition, okay? So why I say that? Now, let's go back to think about the radiation. I mentioned this before here again, right? So I have this imaginary detector. I can put there on one side it absorb one type of photon as a T2 and the other side T1. So once I go to the wall, it's still absorbed in this side and the other side. And so far, I have assumed the wall is black. What does black means is on this side, the photon comes in, they just go no reflection. Right? That's a black. Black is no reflection. Everything is coming is absorbed. So it's also transmission. That means the transmission is 1. Right? When transmission is 1, so of course this is solid. A solid, I don't have a way to get into it to put a detector, but imagine you got this magic detector I have, and if it moves into solid, but it doesn't interact with the photon, doesn't interact with solid, they only measure the light, photon, right? What would be the temperature it measure? Huh? So incoming is, so here is here on this side and on this side, both sides, right? So it will be continuous. In fact, there will be no jump if you can do that magic detector. And of course, the solid itself, this photon will have absorption and re-emission in the solid. So what will happen is that this is what you measure, the photon temperature. You would measure, but there you don't have that detector. What you have is a thermocouple, right? And when you put a thermocouple into this solid, what you measure is a solid temperature. That's a photon lattice vibration. Okay, so this is my TE1. What I say is this is the photon temperature, and equivalently, when they emit, I say this is a half of the space they emit as a black body. So that's where my physical temperature jump coming from in the case of photon. Now when I do photon, right, and if the surface, again, is black as what I'm saying, that's immediate at the temperature T1, equilibrium temperature. So transmissivity is 1. There's no, so if there's no reflection, this is a material 1, material 2, material 3. Right? In solid, I typically can do multi-layer structure. And in that case, there should really be no temperature jump. Okay, it's similar. You can actually measure the temperature. Suppose you have a nice way to measure the lattice temperature. So there should be no jump. And this jump is only because I'm assuming the photon coming out is at this temperature. What happens is that this is the interface I discussed before, right? If you look at what comes to this side is TE2, and what TE1 is going out like this, but the TE2, it goes out like this because it's a lower temperature, right? So if you define temperature consistently, you should not have that jump. This is a highly non-equilibrium situation. There's no good temperature definition. Okay? And however, the other solution, this is, again, you can go back to rederive everything. That is when your surface is not black, when your surface has a finite transmission, reflection, right? And this is where you actually have a physical temperature discontinuity at the two interface. And this is what, if you do Boltzmann equation, you can consistently including everything. Okay? And in chapter 5, I discussed this. It's really how you have to be careful how you define temperature when you go to this ballistic or quasi-ballistic regime. Otherwise, you may be comparing apple and orange. Okay? Any questions? It takes a lot of time. People still continue making those mistakes, okay? So if you go to read papers, and then many of them don't distinguish the subtle difference. Okay, so that's the case. So if we think about what we talked, is a transport along the film, transport perpendicular to film. Okay, I'm going to next to tell you a story about mixture. The transport both along and perpendicular to the film. What would be the case like that? Huh? This is a fluid flow. Think about you push a fluid through a pipe, air molecules, right? A small pipe. And this is the Poisson flow. So let's look at the case, simplest case. Rarefied. Poisson flow. Okay, so so this is the pipe flow that you are all familiar with, but in the limit of Poisson flow, I say two parallel plates. Between two parallel plates, I'm flowing fluids through. And if one plate is moving, the other plate is stationary, that's a co-ed flow. If it's pressure driven, both plates are stationary, that's Poisson flow, right? You learned that in fluid mechanics. So I'm going to deal with the case where I have stationary plates, I have a fluid flow inside. And in this case, we wrote down the Boltzmann equation df dx, right? This is my x direction, and my y, vy df dy equals to f minus fd over tau. That's my relaxation time. And it's not the f0 because I have a non-zero fluid velocity, average velocity. So it's displaced Maxwell distribution we said before, right? So this displaced Maxwell distribution is n m 2 pi kbt 3 over 2 exponential m v, that's the random velocity, minus u, which is a function in the case of laminar flow is 2 u is a function only. U is changing in the x direction, but it's a function of y, right? That's the pipe flow. In normal is a parabola. And is y is my coordinate. U is the flow, average flow direction. So u is a function of y, but is in the x direction, right? So flow is in the x direction. My constraint is again in the y direction. That's a finite thickness, right? And it's pressure driven. So where does the pressure come in? It doesn't come into my Boltzmann equation. Pressure, in fact, is a statistical average, just like temperature is mechanical, right? Statistical average on the momentum. But in this case, here, it can relate to n is a function of x, and then you can use ideal gas n as a PV equals nRT, right? So this is you relate this molecular density to the pressure. I have to say that I'm not satisfied with this approximation. So ideally, I would not even do that. I would say, okay, my pressure is just a momentum average. I tried to do that. I was not successful. Okay. So this is the classical. You put in the Boltzmann equation now. It's both in the x direction. I have u, and then in the y direction and the nx, I have the source term in the x direction, pressure, and then in the y direction, I have the boundary. And if you plug in into the equation, you will find out that you need to do the same thing as we did for the perpendicular transport. Because u, that's a velocity distribution, is we do not know. Average velocity distribution, just like when you try to find temperature distribution. U is a function of y. And so it's u is inside the integral. It's an integral equation over u. When you do everything derive, just follow the same way. Okay? So what is interesting is out of this problem is a Lucent minimum. So this was observed experimentally in 1905 or 1906, this period, by Lucent, doing rarefied gas flow. And what they observed is if you plot your flux, say mass flux, right, which is normalized, say 2R ideal gas constant, 0, and the d square. D is the thickness of the plate, and the real measured flux, and dp dx. So this is long dimensional. And what it has is, and this is drawn as a function of Lucent number, which is the inverse. Lucent number is the mean free path over d. That cosine I mentioned before is d over mean free path, right? In different fields, there are different names. For example, inverse of this is called, in optics, called optical thickness. In acoustic, we also call acoustic thickness. But this inverse mean free path over d is a Lucent number. And that's one has the longest history. So if you say Lucent number for photon, Lucent number for electron, that's all fine. You just need to follow the same mean free path over the thickness, over the characteristicness. There are people actually call the wrong inverse as a Lucent number. That's wrong. Okay, so what they find experimentally is that it goes this way. And this is when this is about 1. This happens around 1. And when you go so here, very small Lucent number, that's a continuum. Very large Lucent number, that's a rarefied gas flow. And in between, there is a minimum. And this minimum calls a Lucent minimum. This was experimentally found out. Okay, so I said that around 1900, and there was no solution. People try to do approximate solution of Boltzmann equation. And it was really until 1960 or 1950, and there's a great mathematician, and he solved the problem. It's a Sersignani. He solved this problem, Boltzmann equation, this way. I just written down. Like y direction, you find the velocity. And they found that indeed this solution has a Lucent minimum. And the reason for this, I try to come up with a very direct picture, right? And the reason is this. You have a pressure-driven flux going in the x direction. And we see in heat conduction, it's always the roughness always decrease the thermal conductivity, right? But see here, actually you got a regime where in the very dilute regime, your pressure is pressing this fluid much faster. So the boundary effect is actually the scattering at the boundary is less important, and that's why you have the recovery of this, flux, the fluid mass flux there. Okay? And then corresponding to this solution, you go to look at your velocity distribution in the pipe or in the parallel plate. You actually find this is where the name actually comes from, right? We know that typically when we do a fluid problem, you see velocity is a long slip boundary condition. But the Boltzmann equation will tell you actually this is 0. The velocity has a discontinuity at the wall. So this is the velocity. There is actually a slip happens between the fluid at the wall. Okay, so this is the slip, velocity slip, and in the next lecture we'll actually discuss. People have tried the various. Let me say, if you do rarefied fluid or you do fluid mechanics and microfluidics, you will add artificial velocity slip, and in fact you add the first order and second order velocity slip to try to accommodate and say. It turns out that the first order velocity slip typically can go to this regime. It cannot go, say, Lucent equals 1 or even higher. Second order velocity slip, you will over-predict the velocity, the Lucent, say, this range. So even in those days, there are people still trying to write the boundary condition. And I'll tell you a story how I derive a new boundary condition next lecture. But that's the this is the Lucent flow and the rarefied pulsate flow Lucent minimum. And let me tell you a story. I mentioned many times that the disk drive, right? The disk drive industry, and the disk drive is a lubrication problem. So what it has is this is a disk. Lubrication problem is typical Rayleigh's equation. And the Rayleigh's equation, how it is basically the rotating disk is a magnetic head. And this magnetic head has an inclination, right? So it's like an airplane. You have an angle, so that gives you lift. And that lift is very important because otherwise your head will crash the disk, right? And this disk is rotating about 10,000 RPM, very fast. It's about 10 years ago, I have a friend, they said, can you look at this problem? We have 1 nanometer separation that we cannot predict. At that 1 nanometer, they already long for, they have not used the continuum. They actually use the Boltzmann equation solution for the flux. So they use Sersin-Gilani solution. Because this problem is, so you're stationary, so you can roughly say this is your movement plate. It's a combination of two. It's a pressure because when you have an angle, if you don't have an angle, that's a Couette flow. When you have an angle, you have a pressure difference built up. So it's pressure will drive in pulsate flow. So it's a superposition of Couette and pulsate flow. So they have not used they have been using the Sersin-Gilani solution, and there was a famous paper for this disk drive problem that decomposed into. But they say there is a 1 nanometer problem. I said, what cares? 1 nanometer, why you need it? Turns out that because at the time I mentioned, they were about 20 nanometer fly height, right? And now this fly height I'm mentioning also to you is about 1.5 nanometer. Okay, that's why it's such an important problem. We never find out what's the reason. I mean, say it could be the molecular, it could be absorb the molecule, it could be the molecular final size of molecules, right? And but it's a very relevant technology problem. And nowadays, like say, they're still concerned because you still have a disk and you have a slider there. And finally, there is another problem. This is you can think about this. If I have T hot and T cold, I have a small opening. So this opening is smaller than molecular mean free path. The question is, what's the flux direction? What's the mass flux going? From cold to hot or hot to cold? maybe we'll discuss in the next lecture. You can think about this. I'll ask you at the beginning. Huh? But I want the let flux.